So let us see this edge linking and boundary detection. Ideally, this edge detection techniques they yield or output pixels lying only on the boundary between the regions. But in practice, this pixel set seldom characterizes a boundary completely because of this. Maybe noise breaks in the boundary due to non-uniform illumination, and there may be other effects that introduce spurious discontinuities. Therefore, this edge detection algorithm are usually followed by linking and other boundary detection procedures, which are designed to assemble edge pixels into meaningful boundaries. Right? Therefore, we require this edge linking and boundary detection, since edge detection techniques may have following or as discussed things. The basic idea, if we go to local processing of edge linking, the basic idea is to analyze the characteristics of pixels in small neighborhood, maybe 3 by 3, 5 by 5, for every pixels xy that has undergone edge detection. And then all points that are similar they are linked. They form boundary of pixels that share some common property. So there are two principal properties of establishing similarity. First is the strength of the response of the gradient operator, which is used to produce the edge pixels, and then the direction of this gradient. This is given by tan inverse gy by gx. Now an edge pixel at xy in the neighborhood which is centered at xy is similar to the magnitude to the pixel at xy when this gradient of xy and gradient of this xy and x dash y dash, the difference of these two is less than or equal to some threshold t. This t is our predefined threshold. An edge pixel at x dash y dash, different position, in the neighborhood centered at xy is similar to the or similar angle to the pixel at xy if the angle at xy minus the angle at x dash y dash is less than or equal to some predetermined angle threshold. So point in neighborhood of xy is linked to xy if both this magnitude and angle criteria both are satisfied. Then we come to this global processing. As we have just seen local processing, we come to Hough transform. You can spell it like Hog or Hough, it depends on you. So now consider this global relationship between pixels. Suppose that for n in an image or n points in an image, you want to find all the subset of these points that lie on straight lines. Now we consider a point xi, yi in the equation of the straight line. Y is equal to mx plus c, y is equal to ax plus b. This is the equation of the line. So there are infinitely many lines which pass through this xi, yi, all satisfying the equation for this varying a and b. This m can be changed and c can be changed if you are well conversant with y is equal to mx plus c. However, we are writing the equation as b is equal to x minus xa plus y, just rearranging it. And considering that AB plane, which is also called as parameter space, yield the equation of a signal line for a fixed point xi, yi. Right? We have just changed it, and now for us, this AB is a plane, not xy is a plane. This AB is a plane. Now this can only be a single line because there is a single plane. Now a second point xj, yj. This also has a line in the parameter space which is associated with it. So these lines intersect. This line actually intersect the line associated with this xi, yi at certain a dash b dash, where this a dash is the slope and b is the intercept of the line which is joining xi, yi and xj, yj in this xy plane. So in fact, all points that lie on this line, this is xy plane, this is a b plane, right? This is xi, yi, this is the line which is joining them. So all points that lie on this line having corresponding lines in the parameter space that intersect at a dash b dash. This is the intersecting point. this is b is equal to xi minus xi a yi. This is just a rearrangement of y is equal to a y is equal to ax plus b. This is another version for some other xj yj. So the common point is, if this is the line at AB plane, this is the line at xy plane, this is another line at AB plane, they intersect at some point a dash b dash. So the computational attractiveness, because in Hough transform we have accumulator cells, this computational attractiveness of the Hough transform arises from this subdivision of the parameter space into accumulator cell. Now this is the this was our AB plane, which we are calling as parameter space because AB are parameter. Now these are the accumulator cells. A min, A is A max, B min, B max. These are the cells. These are the expected ranges of slopes and intercept values. Now the cell at coordinate ij with cell value at aij correspond to some square associated with parameter space coordinates ai bj, like this, some or the other. The collection of this accumulator cell is commonly called as Hough matrix or Hough array, and these are computed as cell. These we set all cells to 0, and for every point xk yk in this image plane, let a equal each of the allowed subdivision values on the x-axis, and we solve for b using this equation, right? For every xk yk, we have to start with the image plane. We need to let a equal each of the allowed subdivision. There are subdivisions on this a axis and solve axis a axis, and we make a subdivisions and we solve for b using this equation. Now the resulting b's, they are rounded off to the nearest allowed values of the b axis. Now if a choice of this AP result in solution BQ, any AP, any BQ, then we let APQ is equal to APQ plus 1. And at the end of the procedure, the value of M in Aij, means value of M in this Aij, correspond to M points in xy plane lying on the line y is equal to Aix plus Bj, right? So the accuracy of the collinearity of this point is determined by the number of subdivisions in this AB plane. So a problem with this representation is that the slope and intercept approach in infinity as the line approaches the vertical. Means vertical lines have some problem with slope and intercept. So we use the normal representation of a line which is given by x cos theta plus y sin theta is equal to p. We also say this is a polar form of the line. This is the polar form of the line, where this is the intercept, this is the theta angle. Now the plane will be with this rho, you can say, or p, you can say rho and theta. So instead of straight lines in AB plane, we now have sinusoidal curves in this p theta plane. This m collinear points which are lying on this line will be like this, okay, for different theta and different rho. This yields m sinusoidal curves that intersect at some value in the parameter space. So the range of this theta is from plus 90 to minus 90, which is measured with respect to the x-axis. A horizontal line has theta 0, vertical line has theta 90, and with rho equal to the intercept, x-intercept, with this rho will be y-intercept, or theta is equal to 90 degree with rho equal to negative y-intercept. The range of rho will be equal to plus minus under root 2d, where d is the distance between the corners of the image. Now this is a Hough transform MATLAB code. You can pause and you can try to implement it. Now this is an image A. This is column map of 256. This is the original image matrix. Now this is the image of the Hough array. This is Hough array. And this is the Hough array which has been formed. This is the transform, Hough transform. And now this is the image, this original image matrix, and this is image of the Hough array again. This is again the transform, which this actually is coming from this code which I presented you, right? So these are the results. Again, this is the another image, and this is the Hough transform, and this is the original image. Again, a Hough transform. Again, the original image, and this is the Hough transform. So this is the Hough transform of basically the image. It helps in this edge linking and boundary detection. Thank you.